Hi all, welcome to MACM 101 tutorial 8. In this tutorial, the topic we'll be covering is mathematical induction. So let's start with the basic understanding of what exactly is a mathematical induction. So it's a mathematical proof technique, and we use it to prove that a statement P of n holds true for every number given the restraints. Like in this question, we have uh, it as n greater than equal to 1 or every positive natural number. So mathematical induction consists of two cases. The first is the base case, where we prove that the statement is true for the smallest value. Again, in this question, it would be n equal to 1. And the second case is the induction step. It proves that if the statement holds for any given case n equals k, it must hold for the next case n equals k plus 1. So if you are able to prove that by the principle of mathematical induction, we can say that this holds true for all n's. So let's start with the first problem. It asks us to prove each of the following for all n greater than equal to 1 using principle of mathematical induction. The first question is 1 square plus 3 square plus 5 squared, so on till 2n minus 1 whole square, which is the sum of all odd numbers squared, is equal to n times 2n minus 1 times 2n plus 1 divided by 3. Now, this would be our P of n, and for this, we'll start with a base case, assuming n equals 1, and then go on with the inductive hypothesis and the inductive step. So let's write the base case. So our basis step would be for n equals 1. P of 1 would be on the left hand side, it's just 1 squared. And on the right hand side, it's 1 into 2 minus 1 times 2 plus 1 divided by 3. So 3 over 3, that gives 1. So since left hand side is equal to right hand side, we say it's true for n equal 1. So our basis step holds, and we can move on to the hypothesis. So with the hypothesis, let's assume that it's true for n equals k. So our P of k would be 1 square plus 3 square plus 5 square, so on till 2k minus 1 squared, and would be equal to 1 over 3 into k times 2k minus 1 times 2k plus 1. Now, after the induction hypothesis, we write the inductive step. Here we try to prove for P of k plus 1. So P of k plus 1 would be 1 square plus 3 square plus 5 square, so on, plus 2k minus 1 square plus 2k plus 1 square. So this is the next term after 2k minus 1, and it should be equal to 1 over 3 times k plus 1 times 2k plus 1 times 2k plus 3. So we take the left hand side. Now this is equal to 1 square plus 3 square plus 5 square so our second last term would be 2k minus 1 square, and the last term is 2k plus 1 square. And the this part would be the inductive hypothesis. So we can replace this with the right hand side of the inductive hypothesis because we are assuming it is correct. So that would be k times 2k minus 1 into 2k plus 1 over 3 plus 2k plus 1 square. This is the last term that was left out. Now taking the LCM, so 2k plus 1 is common here, we take it out. This leaves us with k times 2k minus 1 plus 3 times 2k plus 1. So solving this bracket gives us 2k square plus 5k plus 3. Now if you're not sure how to solve it further, what you can do is solve the right hand side of the inductive step, of the k plus 1th term, and that should essentially give you this. So if you multiply k plus 1 into 2k plus 3, that gives us 2k squared plus 5k plus 3. And since left hand side is equal to right hand side, we prove this for n equals k plus 1. Therefore, by the principle of mathematical induction, P of n holds true for all positive natural numbers or all positive integers. Now looking at our next question, it was summation I equals 1 till n 1 over I times I plus 1 is equal to n over n plus 1. So again, here we start with the basis step. Our base case would be P of 1. So left hand side is summation I equals 1 till 1. That means just one single term. 1 over I times I plus 1, and it's equal to 1 over 2. And the right hand side would be 1 over 1 plus 1, and it's equal to 1 over 2. Now since left hand side is equal to right hand side, P of 1 is true, so we can move on to the induction hypothesis. Now in induction, you need to remember all these 3 steps, and they are very essential. So the first one is basis, second one is induction hypothesis, and the third one is inductive step itself. So in the first, you take the smallest term possible and verify if it's true. In the induction hypothesis, we assume P of k to be true. So here we assume summation I equals 1 till k is true for some arbitrary k which is a positive integer. And in the inductive step, we'll try to prove that the next term, which is k plus 1, is true. So here we need to show summation I from 1 till k plus 1. One over I times I plus 1 equals k plus 1 over k plus 2. Now again, here we take the left hand side. Now this can again be split up to summation from 1 till k and adding the k plus 1th term to it. So the summation would be from I equals 1 to k, and the k plus 1th term is 1 over k plus 1 times k plus 2. We are just substituting k plus 1 in I. Now the first part comes from the induction hypothesis, and we can rewrite it as k over k plus 1, and the second part is left as it is, 1 over k plus 1 times k plus 2. So the LCM here would be k plus 1 times k plus 2, and the numerator becomes k times k plus 2 plus 1. Now when we open the braces, it gives us k squared plus 2k plus 1. And this is k plus 1 square. So rewriting it as k plus 1 square over k plus 1 times k plus 2. So 1k plus 1 gets deleted, and this leaves us with k plus 1 over k plus 2, which was the right hand side in the inductive step which we wanted to prove. So we say p of k plus 1 is true, and therefore by the principle of mathematical induction, p of n is true for all n belonging to positive integers. Now for our third part, it was summation I from 1 to n, I times I factorial is equal to n plus 1 factorial minus 1. I hope you know the definition of factorial. It's, let's say you want 3 factorial, that would be 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So now we start off with the basis step. Here we'll take p of 1. Now our left hand side is 1 times 1 factorial, and that's 1. And right hand side is 1 plus 1 factorial minus 1. So 2 factorial is 2 times 1, which is 2. 2 minus 1 leaves me with 2. Sorry, 2 minus 1 is 1. Now the left hand side is equal to right hand side, so p of 1 is true. Moving on to the induction hypothesis. Now here again we assume p of k be true for some k belonging to n greater than or equal to 1. So summation I from 1 to k, I times I factorial, and it should be equal to k plus 1 factorial minus 1. Moving on to the inductive step. So here we have to prove p of k plus 1. Now it's not always necessary to write p of k plus 1 as this term, but it's a good idea to have a visualization of what you need to prove. But don't forget to write the words to prove in the beginning. So here we are to prove p of k plus 1, which should be equal to k plus 2 factorial minus 1. Now again we take the left hand side, and which is equal to summation I from 1 to k plus 1. So I made a mistake here. It should be I times I factorial. Now I'll be updating this soon enough. But yeah, so when we have the left hand side, we split it up from k plus 1 to summation till k and add the k plus 1th term in the end. So now our equation has two parts. The first is summation from 1 till kth term, and the second part is the k plus 1th term itself. Now this usually works because you already have the summations or such stuff till kth terms from the induction hypothesis, and all you need to do is add the k plus 1th term to your already summed up values and see what the solution is. Now replacing this summation with the solution from induction hypothesis, which is k plus 1 factorial minus 1 plus the k plus 1th term, which is k plus 1 times k plus 1 factorial. Now you can take k plus 1 factorial common, and that would be 1 plus k plus 1 minus 1. So now it's k plus 1 factorial times k plus 2 minus 1. So just as we know, if we multiply 4 into 3 factorial, it's essentially equal to 4 factorial. So exactly same in the same way here, k plus 2 times k plus 1 factorial is equal to k plus 2 factorial. So k plus 2 factorial minus 1 is the right hand side, and that's what we required. So by the principle of mathematical induction, p of n is true for all n greater than equal to 1. Now for our second question, we are supposed to prove the Moivre's theorem, which is equal to cos theta plus iota sine theta to the power n, and this is equal to cos of n theta plus iota sine and theta. Now iota is a complex number, so for this problem all you need to know is iota square is equal to 1. Um, just as we read in high school, uh, square roots exist only for positive numbers. They do exist for negative numbers as well, but the square root is an imaginary number or a complex number. So that's where iota comes into play. So for the base case, we have cos theta plus iota sine theta to the power 1. And our right hand side would be, now replacing n as 1, it will give me cos 1 theta, which is cos theta, plus iota sine theta. Now our left hand side is equal to right hand side, so P of 1 is true. We move on to the inductive hypothesis. Here we just assume that P of k is true for some k belonging to positive integers. So cos theta plus iota sine theta to the power k should be equal to cos of k theta plus iota sine k theta. So to prove this, we'll start off with the left hand side. Again, our goal would be, now since this is not a summation, we won't be able to write the sums as like breaking it off, but our basic goal would be to somehow try and substitute the uh, induction hypothesis into the induction step itself. So here we are supposed to prove P of k plus 1, which is cos theta plus iota sine theta raised to the power k plus 1. Now we start with the left hand side as usual. The only thing we'll do here is split k plus 1 into 2 multiplications. So let's take an example like 2 to the power 2 plus 1 can be written as 2 to the power 2 multiplied by 2. So in the same way here, we'll write cos theta plus iota sine theta to the power k plus 1 as a multiplication of cos theta plus iota sine theta raised to the power k multiplied by cos theta plus iota sine theta. Now you can replace the inductive hypothesis here. So this leaves me with cos of k theta plus iota sine k theta multiplied by cos theta plus iota sine theta. Now we can open them up distributively. So this will leave me with cos of k theta multiplied by cos theta plus iota sine theta plus iota sine k theta multiplied by cos theta plus iota sine theta. Now once we open these brackets again, it gives us cos k theta times cos theta plus cos k theta times iota sine theta plus iota sine k theta cos theta plus iota sine k theta, so iota square sine k theta sine theta. Now iota square, as I told you, it's -1, so we replace it here. And rearranging the terms, it gives us cos k theta cos theta minus sine k theta sine theta plus iota times cos k theta sine theta plus sine k theta cos theta. Now here are two rules from trigonometry which come into play here, which is cos of a plus b, and it's equal to cos a cos b minus sine a sine b, and which is the first half of our equation. And sine of a plus b is equal to sine a cos b plus cos a sine b, and that looks like the second half of our equation. So using these rules, we can rewrite the above as cos of k theta plus theta, so k theta is the a and theta is the b, plus iota sine k theta plus theta. Now theta is the common term here. Taking it out, it leaves us cos k plus 1 theta plus iota sine k plus 1 theta, and which is the desired right hand side. So p of k plus 1 is true. Therefore, by principle of mathematical induction, the result is true for all n greater than equal to 1. Now our third question, it says, prove that for all natural numbers n, if n greater than 3, then 2 to power n is less than n factorial. Now n greater than 3 is a restriction here, so our basis would start from 4. So the next natural number is 4. You could also write this restriction as n greater than equal to 4. That's one and the same thing. So our basis is p of 4. Left hand side is 2 to power 4, which is equal to 16. Right hand side is 4 factorial, and it's equal to 24. So 16 is clearly less than 24. It holds true. Let's try and see if it would have worked for n equal to 3. So 2 to power 3 is 8, and 3 factorial is 6. Clearly, this doesn't hold. So yeah, our basis would be 4. So from 4 onwards, it should hold true for all natural numbers. Now, in our inductive hypothesis, we say let p of k be true for some k greater than 3. Or you could have written k greater than equal to 4. So it's 2 to power k is less than k factorial. And in the induction step, we have to prove p of k plus 1. So 2 to the power k plus 1 should be less than k plus 1 factorial. Now you can start it either way. I would like to start from the right hand side here. So I'm just going to rewrite it as k plus 1 factorial is greater than 2 to power k plus 1. they both mean the same thing. 3 is greater than 2 or 2 is less than 3. It's one and the same. So taking k plus 1 factorial to start with. So now k plus 1 factorial is k plus 1 times k factorial. And now opening it up distributively, it gives me k times k factorial plus k factorial. Now from the hypothesis, I know k factorial is greater than 2 to the power k. So replacing k with 2 to the power k leaves us with k times 2 to the power k plus 2 to the power k. Now we also know from the question itself, or even from the inductive hypothesis, that k is greater than 3 or greater than equal to 4. So we can also replace k in this question with 4. So k into 2 to the power k plus 2 to the power k is greater than 4 times 2 to the power k plus 2 to the power k. Now, we could also argue that since 4 is greater than 1, so I could also write the above equation is greater than 2 to the power k plus 2 to the power k. So adding them up, it gives me 2 times 2 to the power k, or 2 to the power k plus 1, which was our right hand side. So k plus 1 factorial is greater than 2 to the power k plus 1. Therefore, by a principle of mathematical induction, it's true for all integers n greater than 3 or n greater than equal to 4. The fourth question says a jigsaw puzzle is put together by moving pieces that fit together into blocks. A move is made each time a piece is added to a block or when two blocks are joined. Use strong induction to prove that no matter how the moves are carried out, exactly n minus 1 moves are required to assemble a puzzle with n pieces. Now here, strong induction is talked about. So what exactly is strong induction? Now, in our previous mathematical induction, we just assumed P of k is true. Now, in the strong induction, we assume P of 1, P of 2, till P of k. They are all true. So that's the only difference between principle of mathematical induction and principle of strong induction. In one, you assume P of k to be true, and in the other, you assume everything up to P of k to be true. So here we are given a move is the joining of two blocks or adding a piece to a block. And we are supposed to prove n minus 1 moves are required to assemble a puzzle with n pieces. Again, we start with the basis step, which is P of 1 is true because a puzzle of one piece requires 0 moves. As it's already complete, you don't need to join any piece or anything else. You just leave it there and it's already complete. So in the inductive hypothesis, we say let P of 1, P of 2, till P of k all be true. And now for the inductive step. Now here we need to prove P of k plus 1 is true. So everything up till now is same except the hypothesis. Here in the inductive step, now the last move consists of joining two blocks with one block has j pieces and the other would have k minus j plus 1 pieces. So this is an assumption we are starting off with. So if our puzzle has k plus 1 pieces, we assume that the last step was joining two blocks with one with j pieces and the other with k minus j plus 1 pieces. Now, since they both are less than k, so I can say P of j is true because of the inductive hypothesis. So we need j minus 1 moves to create a block with j pieces. So there was a mistake in the video. It should be j minus 1 moves to create a block with j pieces. And since P of k minus j plus 1 is also true, we need k minus j plus 1 minus 1. That is k minus j pieces. Sorry, once again, it should be k minus j moves to create a block with k minus j plus 1 pieces. Now, adding these two moves, number of moves plus 1, which is joining these two, is equal to k. Therefore, P of k plus 1 is true since it requires k moves to assemble a puzzle with k pieces. So your first block required j minus 1 moves, your second block required k minus j moves, and joining them together required one more move. So summing it all up leaves us k. Therefore, P of k plus 1 is true. So by the principle of strong induction, P of n is true for all positive integers n. Moving on to fifth question, it says, give a recursive definition of Pmn, the product of integer m and non-negative integer n. So Pmn is m times n. Now, P of n minus 1 would be the product of m and the non-negative integer n minus 1. So for recursion, all we need to have is product of n in terms of n minus 1. So here we have P of n minus 1 as m times n minus 1, which is mn minus m. And P of mn was m times n. Now I can add m and subtract m from this. The first part is P of n minus 1 plus m. Now for recursion, we also need the first term where to begin the recursion with. or where to exactly end the recursion. So because P of n is broken as n minus 1, n minus 1 would be in terms of n minus 2 and so on till n0. So P of 0 would be m multiplied by 0, which is equal to 0. So the whole recursive definition is Pm of 0 is equal to 0. Pm of n is equal to Pm of n minus 1 plus m when n greater than equal to 1. And that's it. For the sixth question, we have a complete binary tree is a graph defined through the following recursive definition. The basis is single vertex is a complete binary tree. The inductive step is if T1 and T2 are disjoint complete binary trees with roots R1, R2, then the graph formed by starting with root R and adding an edge to the vertices R1, R2 is also a complete binary tree. So here, this is just a vague example. So we had two binary trees, we joined their roots together, and that's another binary tree. Now we are asked to draw all complete binary trees that can be obtained by applying inductive step at most 3 times. So one would be the level 1, which is taking 2 root nodes and then joining them together. This gives you level 1 binary tree. Level 2 binary tree takes 2 level 1 trees and then joins them together. And level 3 takes 2 level 2 trees and joins them together. Now, the other part of the question is use structural induction to show that n of t is greater than equal to 2h of t plus 1. N of t is the number of vertices in the tree t, and h of t denotes the height of the tree. Now, structural induction is used to show results about recursively defined sets. There we say in the basis we prove the statement holds for all elements in the basis of the set definition, and in the recursive step we prove that the statement holds true for each of the elements used to construct elements in the recursive step, and it holds true for the new elements as well. So here in the basis step, let's take R to be a complete binary tree consisting only of root node. So here the height of a tree with just one node would be 0. So 2 times height plus 1 is 1. And n of R means the number of vertices is also 1. And 1 is greater than equal to 1. This claim holds for the tree R. So here in our inductive hypothesis, we'll take 2 trees T1 and T2, which are complete binary trees, and assume n of T1 is greater than equal to 2 times h of T1 plus 1. That is, number of vertices in T1 is greater than or equal to 2 times height of tree plus 1. And the same goes for tree 2. In the inductive step, or you could also say the recursive step, we'll take T as the combination of T1 and T2. So let T be a complete binary tree. We need to prove that this expression holds true for the tree T, because T is itself made of T1 and T2, and since we assume T1 and T2 hold the equation true. So the combination which is making up the tree T also holds true. So n of t is equal to n of t1 plus n of t2, that is number of vertices in both trees, plus 1, which is the root node. Now, since we have the inductive hypothesis over there, we use that inequality to replace them here. Now, n of t is greater than equal to 2 times h of t1 plus 1 plus 2 times h of t2 plus 1 plus 1. Now, height of t1 plus height of t2. So for any two non-negative integers, x and y, uh, it's safe to say that x plus y would be greater than or equal to max of x or y. So that is basically saying 2 plus 3 would be greater than equal to 2 or 3, whichever is the max. So in this case 3. So here we can say n of t is greater than equal to 2 times max of height of t1 or height of t2 plus 1 and plus 1. Now, when you join two trees together, the height of the new tree is equal to max of height of either trees plus 1. So if one tree had a height 5 and the other tree had a height 6, so your new tree will have a height 6 plus 1. Now this 1 comes from the root node which we are adding. So we add one more level. Therefore, this n of t is equal to 2 times h of t plus 1. And we can say the claim holds true by structural induction. And that's the end of the proof. So that's all we had for this week's tutorial. See you guys next week.